In this chapter, we will go through some general steps involved in decision analysis. We'll also cover different types of decision making. We'll cover decisions that are made under uncertainty and decisions that are made under risk. And we'll also cover a tool called decision trees that are very useful for making decision analysis. So as you know, every company is involved in making decisions from time to time. Some decisions are very, very successful, and sometimes the decisions are not that successful. Now, one important thing in making decisions successful for any company is a lot of quantitative analysis that they do so that the decisions are based on facts and they are not like guesswork. Some very general steps involved in decision analysis. So it always starts with defining a problem. So it has to be very clear what exactly we want to analyze, and then we list different alternatives that may exist. Once the alternatives are listed, we also identify various outcomes, or and then we list down what will be the payoffs depending on what alternative we choose or what state of nature exists. The next step is to select a math model, and then we apply that model and make decisions. So these are some of the generic steps involved. Now let me take one example to go through and explain how these steps really work. Now this example is from your book, and this is about Thomson Lumber. If you read the example, this company wants to expand. They want to create more products which can reach different customers. They have three different alternatives. One alternative the owner of the company has is that they can go for a large plant with this new offering, so they can produce a lot of new items, or they can go for a small plant, so this is not that ambitious. And many times people ignore, but it is always one of the alternatives is to do nothing. So the third alternative is no plant. So the first step was define problem. So basically the problem is to reach more customers with a new product, and they have listed three alternatives: large plant, small plant, and no plant. Now the next step is to identify outcomes or state of the nature. Could be either favorable to this new product or unfavorable. So favorable means obviously that the product will be very successful, there will be a lot of demand, and this company will be able to sell more and more of these products. And unfavorable means that the demand will not be that strong. Next step is to list payoffs. Now let's say they have collected data and they find that if they use a large plant and if the state of nature is favorable, they can make, so this is the payoff. If they go for a small plant and if the situation is favorable, similarly, if the state of nature is unfavorable and they go for a large plant, they make a loss of 180,000, because whatever investments they make in the large plant and they make those products, if they do not sell, they will have a big loss. With small plant, there will be a loss, but it will be smaller. And if there is no plant, obviously there is no loss. That is listing payoffs. Now, depending on the situation, one may select a particular math model and also apply the model. So we'll spend more time on that as we go forward. In a way, actually, that also depends on what is the decision-making environment. So in fact, there are three different decision-making environments. Certainty. So certainty means that we know for sure what will be the outcome. So let's say you have $1,000 and you want to invest it. You can invest in, let's say, a savings account in a bank, or you can invest in a certificate of deposit CD, which pays slightly higher rate of interest, or you just keep it with you. So for each of these situations, outcome is certain. You know that if you deposit in a savings account, how much money you are going to make. So every bank has their own interest rates, and right now it is quite low, but let's say I'm just putting some hypothetical value, although it could be less than that. So you may get 1% by putting the money in savings, and obviously slightly higher, maybe 2% by putting in CD, and maybe 0% if you do nothing. One thing is known, that at least you will not lose any money, and also there is a certainty that you have either 1% or 2% or no payoff. So difference between uncertainty and risk is, whereas decision making under risk, probabilities are known. That's the key difference. So if you put your money in the stock market in a company, the price of that company may go up or it may go down. So we don't know like what is the probability of the market going up or down. It is very, very unpredictable. A lot of uncertainties exist, and there are so many variables impacting the stock prices that it is almost impossible to attach a value of probability to the stock market. So in that situation, obviously, we make decisions under uncertainty. However, there are situations where probabilities are known. For example, if you take a dice, so as you know, dice has 6 sides. What is the chance, like if I throw a die and we get a value of 3? So because it has 6 sides, the probability is 1 by 6. Similarly, if you take example of cards, now what is the chance that if we draw one card randomly and it turns out to be an ace? So that probability, because we have 4 aces in a pack of cards and there are 52 cards in all, so that probability is 4 over 52. So in these two examples, you can see that the probabilities are known. We know what is the probability of getting certain outcome. So these type of situations are called decision making under risk. In this chapter, we'll cover uncertainty and risk situations. So if we take that example that we started with, so we have alternatives. So the alternatives are, either we go for a large plant, LP, small plant, SP, no plant, NP. We have two states of nature. One is favorable market, so FM, and unfavorable market, UM. And we have the payoffs, and we are assuming that we are making decision under uncertainty. So for making decisions under uncertainty, there are different criteria one can use. One of the most commonly used is called maximax. It is also called optimistic criteria. So basically, the idea here is to maximize the maximum profit. So first of all, you find what is the maximum payoff in each row. So for example, in the first row, maximum value is 200,000. Then you have 100,000 and then 0. So out of the three, maximum is 200,000. So that means if we are using maximax criteria, the decision is to go with large plant because that will result in maximum profit. Another criteria is maxmin, and this is called pessimistic criteria. So in the first row you have 200 and negative 180,000. So minimum payoff is 180,000. Similarly, negative 20,000 and 0. So now we choose maximum of the three. Maximum of these three minimums is 0. So in this case, somebody using a pessimistic approach will go for no plant based on this data. There is another criteria called realism, also named as hurwicz criteria. In this criteria, there is a coefficient called alpha. This symbol here means this is a Greek alphabet, alpha. When alpha is 0, it implies maxmin. And when alpha is 1, it means maximax. It is again a special case when it becomes optimistic criteria. In reality, based on this criteria, the value of alpha will be somewhere in between those two. Using that, we can calculate what is called a weighted average. Calculating weighted average is very straightforward. So just as an example, let's say we are using this criteria of realism with alpha equals 0.8, which means we are slightly more towards optimistic. How do we calculate the weighted average? So if you consider LP or large plant, so alpha is 0.8 times 200,000. So this will give you, so this is the value or weighted average that we get, 124,000. If you repeat the same calculation for the second row, you should get 76,000, this is 6, and this is 0, and then you take the best of the three, which is 124,000. So basically based on this, we go for large plant. There is another criteria, and this is called equally likely. So equally likely means we assume that whether it will be favorable market or unfavorable market, we assume that both are 50-50. So alpha becomes 0.5. So again, if you do this calculation for large plant, if you calculate the weighted average, and if you do the same calculation for small plant, we'll get 40,000. So the best payoff is 40,000, so we go for small plant based on equally likely criteria. Similarly, there is another criteria, and this is called minimax regret. So sometimes we are interested in minimizing maximum opportunity loss. To do that, we can remake the table. So we have these alternatives: large plant, small plant, no plant, and we have the state of the nature, SON. What we do is very simple. So for each column, take the maximum value and from that subtract the payoff. So for example, in the first column, maximum value was 200,000. So we do 200,000 minus 200,000, which is 0. And then 200 minus 100 is 100. And also 200,000 minus 0 is 200,000. Similarly, maximum value in the second column is 0. So 0 minus negative 180,000. So negative and negative become positive. Now minimum of the three is 100,000. So it tells us that we go for a small plant because that will minimize the maximum opportunity loss. So as you know, the major difference is that the probabilities are known. So for decision making under risk, we calculate what is called expected monetary value. Expected value or the average value is same as average or mean. The only thing is in earlier example also we calculated expected value or average using weighted averages. But basically we are calculating the average when we talk about expected value. So we have these alternatives and our state of nature. So we are using the same example and same data. Now the only difference is apart from this data we are also provided the probabilities, and let's say they are 50-50, 50% and 50% that the market will be either favorable or unfavorable. Calculating EMV is very straightforward. So we multiply this probability by the payoff and add them. 200,000 times zero point 0.5, so half of 200,000 is 100,000. Similarly, negative 180,000 times zero point 0.5, so half is 90,000. This one is 40,000, this one is 0. So the best outcome is obviously 40,000. So we can go for a small plant. Now let's say there is a marketing firm and they say that they can get you perfect information in terms of what the state of nature will be. So right now we have this probability of 0.5, zero point 0.5 each. But this marketing firm claims that they can give you or they can do some kind of survey and get you more accurate picture of how the things will be. But obviously they will charge money for that, and let's say they will charge about $65,000 to conduct the study. So sometimes we have to figure out whether we should go for that or not. We can always find what is called as, so obviously we will like to know what is that value, and if we find that value is less than 65,000, obviously $65,000 is not worth paying for. But if the expected value of perfect information is more than 65,000, so obviously it makes sense to pay that money and get better outcome. So EVPI is equal to expected value with perfect information minus expected value without perfect information we just now got is this $40,000. So this is $40,000. This is expected value with perfect information, 0.5 times best value. So if it is a favorable market, the best value is 200,000. So multiply 0.5 with 200,000 and then plus in the second situation when the market is unfavorable, the best payoff is $0 because other two situations are negative. So expected value of perfect information is $60,000 and the marketing firm is asking for 65,000. So obviously it is very easy to make a decision what to do. We can also do another calculation just like the previous situation, expected opportunity loss. So I will repeat the table we made for opportunity loss for decision under uncertainty. And we also have P of 0.5 each. So if you do the weighted average calculation for large plant, same thing if you do for small plant, you should get 60,000. The lowest value obviously is 60,000, so we go for small plant. So one thing you'll notice is this value and this value are always same. So basically if we make the last table expected opportunity loss table, you automatically also get a value for expected value with perfect information. So you can get EVPI directly without doing anything different. And you'll also notice that this 60,000, so I will make an arrow here dot with the dotted line. If I go like this to the 40,000, both of these situations always lead to same decision. Same decision means here also we get small plant as the best decision, and in the first situation also we get small plant as the best situation. So in a way, if you do the calculation for expected opportunity loss, you are combining two different calculation into one. So you don't have to do EMV, and similarly you don't have to calculate EVPI. Just with one shot you have both answers. So there is an advantage in using this last table. Let's say P is the probability of a favorable market. So when we have the situation of decision making under risk, and when we say the probabilities are known, they are known, but there could be some small variations in those probabilities. They are not like perfect numbers. So sensitivity analysis allows us to do analysis where we can find out if there are some small changes in these probabilities, what effect they will have on the final decision, or in a way how robust are these decisions in the presence of some small variations in the probabilities. So how sensitive our decision or the final decision is to small changes in the probability, so that we can assess using sensitivity analysis. So for that we calculate expected monetary value for large plant, and you know that let's put P instead of actual probability value in the equation. So 200,000 is the payoff times P plus, so if you simplify this you should get, let's say this is our equation 1. For small plant same thing, and third one no plant, because payoff is 0 times P plus 0 times 1 minus P, and this is our equation 3. So we can actually plot these three equations. Now if you take equation 1, if we put P equals 0 in equation 1, 380,000 term vanishes and we are left with 180,000, negative 180,000. So that point will be approximately here. And if P equals 1, so 380,000 times 1 is 380,000, and minus 180,000 you get 200,000. So somewhere here. So this is for EMV large plant. Similarly, if we use equation 2, if P equals 0, you get negative 20,000, which is somewhere here. And with 1 you get 120,000 minus 20,000, actually you get 100,000, so it is somewhere here. And this line here is EMV no plant. So that is your x-axis. There are 2 points or 2 intersections. One is here. Suppose we label this as A, and there is another intersection between 2 lines at this point. Suppose this is B. So what we can do is to find out the actual value of A and B. We can say for A, so A is based on equation 2 and 3. We can equate. So equation 2 is equal to equation 3, and equation 3 is 0. So value of P equals 0.167 for point A. Similarly for B, So what this all means is very simple. It tells us that if P is less than 0.167, if P is in between, and if probability of a favorable market is more than 60%, or to be more precise, more than 61.5%, then we should go for large plant. So you can see the sensitivity analysis, how it gives you a range for different values of P and what the likely decision is going to be